Okay, so we have started the root finding methods, and just a brief review. What is root finding? Essentially, I format my problem, and problem is typically a physical problem that I have a model for, into a problem that looks like f of x is equal to 0, or f of some other variable is equal to 0, and I'm looking what variable basically zeroes this function out. Okay? And a lot of physical problems can be formulated that way. But most of them, so we had one example that we all know very well and have a formula for, that is the quadratic equation. For a quadratic equation, if I say ax squared plus bx plus c is equal to 0, where a, b, c are given, I know how to find two x's that actually make this function 0. The only problem that I might possibly run into is that these might be imaginary, but they still exist as solutions. Okay? And sometimes actually numerically, if I'm actually computing this, if I have two values that are relatively close, especially if this 4ac is a small number, then there might be a little bit of an issue. That way I'm not going to trip over it. So, yeah, it would be good. It would look good. So anyway, you might have some issues by subtracting two numbers that are too close, but other than that, we have an analytical form. So this problem is not what bothers us. What bothers us is a problem of this type. So we had this falling parachutist problem. Basically, I can relate, I have a parachutist falling down, so there's force of gravity, there is a drag force that is opposing it, and basically parachutist will start in a constant velocity motion as opposed to just being drawn to the earth once I actually have those two in balance. And of course, if I'm a designer of the parachute, I want to optimize this so-called drag coefficient C so that this actually happens quicker and sooner. Okay? That's a better parachute. So I might be interested in modeling this, and since I can actually relate the velocity, I can measure the velocity. Okay? I can use that measurement to actually optimize my C. So often I'm looking for C that does that the best. Okay? And essentially, I can formulate my problem as some function of C, which in this case is a nonlinear function, is equal to 0. Okay. So great, but to find that, I don't have a formula. I need to look for this numerically. And then I commented that the first thing, if you don't know anything about root finding, one thing that you can do is simply plot the function, okay, and inspect the graph, and that's what we did last time around. I hope you still have that in your MATLAB. So if you open it, we essentially, I have that as a roots parachutist of C. In this particular case, I created it as a function. So I should actually create that C, so this is my C values that are somewhere, there's a problem with 0, I don't want to divide by 0, so I'm starting from 0.1 to 20, and then I'm just going to execute F is equal to parachutist of C. I basically just find my values of F. There are two ways to do this. These are equivalent. I can either do it without vectorization or with vectorization. So this is that dot operator, dot divide. And I simply plot it. Just to guide the eye, I plot the function. So this is my function f. I can also plot the zeros, which is this, or just put grid on or something like that. And then I can literally inspect, oops, not rotate. I can inspect this graph and find that the value is close to 14.5. I can also look at the values of f and sort of try to eyeball
So I have positive, positive values. Those are these. Okay. And as I go further, I can see that I go down to 0.35, and then I switch to negative values. So I kind of cross 0 here because my values go from a positive to negative. And I could actually find what is my corresponding C. So this is columns 26 to 30. So this is a F of 30. Okay? And F of 31 is this. So I know what my C of 30 is. It's 14.6, and C of 31 is 15.1. So basically my 0 is somewhere between 14.6 and 15.1. Okay. And that's as close to I can get based on what I computed here. I could, of course, refine my C's and try to get closer. So if I could refine here and go smaller, and then I could actually get closer to that 0 if I wanted to. That's quite a bit of work, kind of like looking into. It's good to plot things. It's good to look into roughly where the values are, but I'd like something a little more automated in finding that 0. And that's what we're going to introduce today. So this is basically my function. Okay, I can inspect the values. I can find those values where I'm sort of like crossing over from positive to negative in this case, and there has to be a 0 somewhere in between. Now, if I don't have the way to plot, I can also simply evaluate. 5 or 10 values is something that is practical to evaluate by hand and get close that way. Now, I can also employ the computer to do this refinement, if you will, and go closer and closer and closer to my 0. So I can see here that, well, I can find the interval, at least the rough interval. And in this case, this could be between 12 and 16. Okay? So for C's between 12 and 16, somewhere in between, I know that I have a 0 because I'm going from positive to negative, and I have a continuous function. I don't have any funky undefined value of f for dividing by 0 or anything like that. So this is a continuous function, therefore it has to hit 0 somewhere in between these two values. So I could actually, so this is formally a mathematical theorem that says that if f has real values, it's continuous on certain interval, and I have a positive and negative value on the ends of that interval, I should hit a 0 somewhere in between. So that I don't think anybody doubts that particular theorem. The problem is that I might have more than one root, but I at least have one. Okay. Now, basically, mathematically, the way you would check for an interval like that is that f of the left side of the interval times f of the right side of the interval has to be negative, because one of them is positive, one of them is negative. Okay? So this is what we're going to use to check in our program that I indeed have an interval like that. So here I have that f of c for 12 is larger than 0, and here it's negative. So basically, positive times negative value will be a negative value. So that is my something to check. And the way bisection method, this is now describing an algorithm that will actually try to zero in, quite literally, on that 0 of the function f. So you have to find the interval to start with, and I have found it. Let's say that it's 12, 16. And then I have to bisect it in half. So essentially, I'm just going to say, okay, I have a 14 here, and I can test whether value at 14 is positive or negative. So in this case, it is what? Positive. So between this value 12, where the function is positive, I'm positive here, and I'm negative here. So what is my next good choice for this interval that is smaller than the initial one? It's staring at you. 14, 16. And I can see that f of 14 times f of 16 is negative. So I have a positive and negative end. So it's still conforming to that rule that I have to have positive times negative value. And on this other end, f of 12 times f of 14 is positive. So it doesn't conform with the rule. Okay? And I can now just keep going. Okay? I have a computer. Computers are good in the sense that you can just tell them to go 1,000 times and do something, and they won't complain. So basically, you can then keep going. So I have 14 and 16. I evaluate f of 15. Is f of 15 positive or negative? Negative. So I have now f of 14 and f of 15 that are positive and negative. Therefore, f of 14 times f of 15 is negative. Yeah? And I can keep going. Yeah? And I'm going to get this interval will get smaller and smaller, and I will presumably get closer and closer to this value where my function is 0. When do I stop? This is a loop. I got to tell computer to stop. Until? Will you get there necessarily? You could, within machine precision, I guess. You can just say, well, stop when this interval is small enough, and you tell it when that is. So if I'm okay with finding this 0 within 0.001, well, I tell the computer to stop then. Okay? We know that at some point computer will add 2 values and there will be no huge difference. So I could actually go within machine precision. It will stop. Okay? What I don't want to do is say, oh, go 1,000 times, because that kind of is not good in the sense that sometimes 1,000 times will be close enough and sometimes it won't be enough. I don't know that in advance. All right, so you know the method now. How about you actually go, so this is formalized algorithm now. Choose left end or lower and upper end of the interval so that my f of xl times f of xu is less than 0. Divide this interval in half. So this is my midpoint. Okay, this method is called bisection. Calculate f of xr and evaluate this function at this middle point. And then based on whether f of xr times f of xu is less than 0 or the other side, I will choose my next upper or lower limit. And repeat until this interval is small enough and you decide what small enough is. So let's work with this function, since this is something that you already have programmed from last time. So I want you to create a bisection.m, okay, that will start from 12, 16 interval as the first choice here. And it can be a script, it can be a function, that's up to you. So I'm actually going to, this is just plotting, so we can actually just continue here, okay? And you can either call this as a different file, this is just plotting it, so it doesn't matter. So this is plot function. And here, say, start from xl is 12, xu is 16. And I want you to implement this algorithm. There's an extra exercise here if you want, but I want you to work with the parachute. It's just because we have it already programmed, so you can evaluate function really quick. And Ningyu and I will walk around and help out. and you will have to submit this by tonight. If you don't have this, it doesn't really matter. Do you want me to upload it if you don't have it? It's just the only thing that it saves you is typing this in. You don't have to plot for now. For this particular part, it's okay. I will go and upload, but you can just keep working on it regardless. Okay. So it's uploaded to Canvas if that's what you want to start from. But this is the algorithm. So one thing that you can note is that this algorithm is really just a common sense. It doesn't really take any big theory. You're just letting computer help you search. Yeah, I already gave you 12 because we looked at it. So that would be the first step, would be to plot the function and see, right? What is a good choice? Or find something by hand. Where is an interval where my function is positive on one end, and that's your starting point of a search. So graphical method you will not use in the sense of like proper search, but just like to look at the problem and decide how to go forward. The graphical, just plotting things, and you're not going to zoom in and find that point because that's manual work. And here we're trying to avoid manual work and program and be smarter. But it can definitely, visualizing things is always helpful, so it can help you find the starting point. And let us know if you need help. This repeat will take a loop. Think about which loop is better. Yeah, you determine some sort, you can call that value epsilon or tolerance or something of that sort. And you keep going until essentially this right-hand side of the interval minus left-hand side of the interval. That means that's your size of your interval, right? It's your length of the interval.
So
upper point minus lower point. Again, you actually decide. In all of these numerical methods, by the way, if the program is not asking you to decide when to stop, that means that it's deciding, it's pre-programmed event. So whoever programmed it decided for you. So that's a takeaway whenever you have numerical methods. They will stop, they will terminate when the solution is satisfactory, and that satisfactory might be decided behind the scene for you. So if you have a problem with the program, that could be a place to search why you have a problem. But it's necessary for any numerical method to have, it's a stopping criterion. It's sometimes called as a stopping criterion. You can't just let computer stop, because it's not going to.
So when you replace XL and XU with that,
So based on whether your f of xr times f of xu is less than 0, or the other choice, what programming construct is that? We use if, else, else if, right? So based on the choice, you're gonna either replace xu or xl. And it might help
To look at this. Is everybody at this stuck at the same point, or? So graphically, I'm gonna calculate this midpoint. I'm gonna call that XR, okay? And then I'm gonna check, okay, if this f of XR that I have, so that's this point right here, times f of xu, which is my upper point, if this is less than 0, that's my interval, correct? So I'm going to replace this point 12 with 14. And this point 12 was XL. So in this case, my XL will move up to be 14, which is my XR. Does that make sense?
So you would say XR equals XL.
Yeah. XL equals XR, because that's your newer value, right? So I here make XR, this is my midpoint. And if you don't mind me, I'll just do everything lowercase. XR is XL plus XU divided by half. So now I'm going to ask myself, first I actually have to compute what is my f of XL, what is my f of XU, right? F of XL is, and this is where I use cut, copy, paste. I'm just going to replace C. It's like, I'm not going to stop sneezing until somebody says bless you. So this is my, I now basically found what f of xu is. Okay. And I'm going to find what all of them are, really. So this is very simple. I'm going to tell you a trick how to be faster here, but now it doesn't matter.
You don't have to do like parentheses XU.
No, because this is a single value. So I don't have, I'm evaluating at a single value. If you do parentheses, you're calling a function. Watch out. F of something, right? There's the programming versus what you would write. Okay. So now I evaluated all this f of xu, f of xr, f of xl. Yes? Everybody clear with this? And this is now just what I'm gonna call a good programming practice. Let's just quickly, I'm gonna copy this into my workspace because this is a function I don't wanna, and I'm just gonna see what these values are just to see that it's correct. So my f of xl, f of xr, f of xu, 12, 14, 16, and then it's 6, 1, minus 2. So yes, I should be fine based on that graph that I plot. It's just double checking. This was around 6, that's fine, and this is around minus 2, that's all right. Okay? So this is debugging on the fly. Because I could have typed in something weird, and then everything else after that is garbage because I had a typo. So check that quickly. And now I'm going to say, what I want to do is I want to say if fxr times fxu is less than 0, do something, okay? Else, if fxr times fxl is less than 0, I can do less than or equal to. Else, I don't know, this would be odd to show up in a case, to have a case when neither of this is less than 0. So I'm just going to say something's fishy here. Just to catch that in future if it shows up as a problem. So this is my decision structure here. Based on this, calculate fxr and then determine which one is less than 0 and replace either end with xr based on what you determine here. But let's see what end we will replace. So if this is my fxr, if this is xl, this is xu, this is xr. If f of xr, so if this is my new interval, then I'm going to move this point, so I'm going to replace xl with xr. Yes? Everybody sees that? Otherwise, I'm going to decide that it's, for instance, if this function was just flipped this way, okay, then I would decide that this is the correct interval. Does everybody see that? So basically the way I write here, so my upper end of the interval is the correct one, so I'm going to move xl to be my xr. Otherwise, I'm going to say, well, xu should be replaced. And I'm going to keep doing this, so this is actually going to be within a loop. Okay. So this is my body. While I can either say xu minus xl. Initially coming in, I have only xu and xl, and I can do that as an endpoint. And so I'm just gonna say in absolute value larger than some tolerance, and I need to define the tolerance. I'm gonna say 0.01 is close enough for me. Is this clear? Questions? This function actually plots things. I'm just gonna change this function now. I'm gonna just plot it, C's myself. I'm just going to return that XR. So I changed this to a function that doesn't have any input, so I'm just going to execute it and see what I get. This is what I get. So this is indeed close to 14.78. So it should be good. Did everybody get here? Let's try to get closer just to see. So if I execute it again, I've changed a little, so I'm presumably getting closer. Just in case that there is a trouble with getting there and there's a while loop here, it is pretty good idea to count number of iterations. Let's see how many iterations we get. So I'm just going to count iterations. And I'm also going to say, well, these iterations are less than 10,000, just in case, to have a guard too. So note, good programming practice. Limit number of iterations. Just so you don't end up with infinite loop that goes on forever because you have a typo or a bug or something. So here I can print what my root is. Oh, I didn't save it. I got there pretty quickly. 16. I certainly didn't hit my 10,000. Yes.
When you started a while ago, why did would you mind going into a while ago?
Mm-hmm.
Yeah. Why is it XU minus XL, not like XR or like something else?
Either way, it's plus minus one iteration. In finding these things, it doesn't matter. Because I'm going to replace. It's the same thing, actually. Because I'm replacing one of them with XR.
Yeah.
So it doesn't matter. And initially, when I'm coming into the loop, I don't have XR. I'm computing XR here. So I wanted to avoid computing it outside and initializing it, essentially. And by the end of this, I'm going to replace one of them with XR, so that's essentially it. Right?
Sorry. Did you define iteration outside? You started it with 0.
I started it with 0, yeah. And then I immediately incremented when I came in. you could start it with 1 and then increment at the very end, either way. Questions? Yes? Sure. So again, key question is actually to plot the function first. So when you're coming in with a different function, plot the function first and see what to start with. Okay? Another thing, and this is a trick that would make this a little cleaner, you can define an inline function. So there are two things to make this a little cleaner. Here, I obviously just copied things 3 times. I could actually have my function f defined outside. Or, so for instance, instead of this, okay, I can actually define a function down here. So for that, I'll need an end to the initial function. Look at how smart MATLAB is. It's showing me the function that I'm ending here. And I'm just going to say another function. F is compute f of c, or whatever is xu. I'm going to use xu. And now I actually have my compute f, and I'm going to use it here. So I'm going to say fxu is compute f of xu. fxl is compute f of xl. And fxr is compute f of xr. So whenever you repeat something like 3 times here and you're going to keep repeating this calculation, it's good to have a function to do it. So if you also want to change the function, you change it in one place, not in 7 other places, right? Another way to do it is inline. But that works. This could be, for instance, function that is outside of the file. I could do it within here. You can say f at, I'm going to do simple function like this, at x is equal to x plus 1, for instance. Whoops. What's the format of this? Inline function. Is it at x, Dingu? Do you remember? No. Okay, I'm gonna quickly remind myself. Inline definition of a function in MATLAB. All right. So it's, if I wanted to define function g, I would say g at x is x plus 1, for instance. So this is just defining function x plus 1, and then I can just say g of 9 is 10. But this inline function just works within that piece of code where I'm executing it. So it's not something that I can have decide outside as a function. So basically this would be inline definition of a function. So I could have done that here with f. You have here a skeleton of a code. Let's see that you understood this. So you have everything. I want you to modify this same problem and solve this one here. So all I'm changing is function f. So using the code you have, you can create that as a script or as another function. You will have to plot this function first to see what to start with, your xl and xu, and then the rest should be very similar to what you just had down. Let's exercise bisection method. And this is the whole good thing about computing. Once you write a solution to one problem, should be relatively easy to modify for a similar problem. You have the skeleton of the problem already.
Yes. Anybody else?
Yeah, I just made it a function.
Jeez, that's wrong.
There's a reason why she added that.
But then I got another problem.
Because she wants to iterate. Yeah. Like, she did actually. I would never type this by myself. Like, what? Why? So it tells you how many times you iterate.
Yeah.
So you go line 25.
Anybody else need to go? Yeah. We'll need to submit this. This one is, the other one I sold. I can post it for you, but.
So for example,
Yeah, so you want to do that, okay, fine. Because you didn't say. Say both of what you need to actually specifically.
Dude, I don't understand what my inner
No, copy and paste.
This is updated one, but I want this.
My
Fishy!
yeah, it's a lot of fishing. I have been fishing.
oh, yeah.
Oh, it should be in stock. Press the wrong.
Not that.
I just pressed the wrong
Oh, it's a sign. Oh, but here.
Oh, okay. Oh, that's
She
another
replaced
one.
this.
Pretty close. I'm gonna create assignment on Canvas by tonight, 11 o'clock.
So basically you just want the parachute script that we did with that?
No, not the one I solved. I want this new one. So, modified parachutist to actually solve this problem.
Right.
Yeah.
Could you
Just see that you understand it. Huh?
could you extend the draw?
Sure.
Because I get off work at 11.
If you submit it by tomorrow 9 a.m., it's good. Okay. I'm not gonna look at it until tomorrow sometime. You're welcome.
Hi,
Mhm.
I had to do a lab makeup